turning search upside down. Firstly, who are we? I run a company called Flax in Cambridge in the UK. We're basically search specialists focusing on open source. We do all kinds of things. We don't have any particular technology we're committed to, but it's generally open source. We're a LuceneWorks partner in the UK, and there's some of the people we've worked for over the years. We also run a search meetup group. If there's not a search meetup group in your territory, go and start one. They're great fun. We have lots of talks and things like that. We've been doing this, some of us, about 20 years. We're pretty experienced in building search applications. So that's me. I co-founded the business. I've been working in search since about 1999 myself. Before that, I did all kinds of other things. And when I'm not doing this, I do other slightly crazy things. Some of you may have seen me destroying some leaks upstairs. There's apparently a picture somewhere on Twitter. And my colleague is Alan, who came to us after working for ProQuest when he had a pretty serious fast ESP cluster to run. And I think you're quite happy you're not doing that anymore.
Yes.
Yes. Alan is a Lucene solo committer. He's so far managed to avoid wearing the blue t-shirt. And he also does other things as well. He sings. We promise not to do any singing or juggling now. So, we have quite a lot of clients in the media monitoring sector, and I just want to give you a quick overview as to what these companies do and why. These are companies where, if you, say you're a business and you're interested in a certain subject, or an individual even, or a football club or anything, you go to these companies and say, right, I'm interested in search engines, I'm in Dublin, Ireland, I quite like open source, and I'd like to monitor some of the technology press, but some of the broadsheet newspapers, but not these ones because they're in Scotland. And so you've got a fuzzy, vague idea of what you're interested in, and the company then sit down with you and try and turn that idea into effectively a query. They give these things different names, and the term I'm going to use today is keyword, which is a bit weird because it's not just one word, it's lots of words, but we're going to call it a keyword. Now, the difference between a standard search application here is instead of doing one query over, say, a few million documents, you might have 10 or 100,000 queries that you want to apply to every single document you see. And the documents are usually news articles. So you can imagine in an innocent fashion that could be quite a difficult thing to scale. 100,000 queries on, you might be monitoring 500,000 documents a day. When you get some matches, when you get some idea that a particular news article mentions your client's interests, you probably don't want to send that automatically to the client because these situations are imperfect, and there's usually some human somewhere in the chain go, yeah, that it really is relevant. And then this article is then emailed or even actually printed out and posted to the end client to say, look, you were mentioned in the paper, or your interests were mentioned in the paper. Where the matches were is very important, because in news, if you're mentioned earlier on in the article, that's actually an indicator of importance, maybe. So, and also, you probably want to highlight where the matches were and why. The end clients can be quite fickle. If you don't get this right, there's plenty of competitors for them to go to. So we've got tens of thousands, potentially, of these stored expressions, these queries, which we're going to call keywords. And these would have been created in particular syntax, whatever original search engine or system you had. Now, the trouble is, you can't rewrite those because you've got so many of them, and if you get them wrong, your customers will start leaving you. So whatever syntax you have at the beginning, you're stuck with. Your teams of people are used to using that syntax. So it's an interesting thing here. We have to cope with whatever syntax the current system is written in when we upgrade these systems and put them in. Again, you've got possibly hundreds of thousands of articles to monitor a day. Some of the source data is nice electronic data. It's XML, it's all correct. However, in the newspaper world, sometimes you're still dealing with paper. It's a slightly crazy situation, but when you have a journalist typing an article into a computer, as we all expect happens, you think you'll be able to get that article off that computer and index it. In the UK newspaper industry, what actually happens is that goes off to some kind of content management publishing system. The paper is printed, and probably there's going to be a PDF of the page. Somewhere on that page is the article, but actually sometimes the article is continued on page 94, so it's on 2 pages. And it's a PDF, and PDF isn't a very good content format. Anyone who's undergone the pain of trying to extract data from PDF format files, yeah, I feel your pain. Now, how do we get this article out of the PDF? Well, what actually happens is that the PDFs are emailed overnight to India, and people manually turn them back into articles, which is completely bonkers. But because the newspaper industry is generally a little suspicious of digital, they don't like this to all be too automatic. So back comes a nice big chunk of XML for each article, which they sometimes get wrong. So there's sometimes faults in the text. And they're often using scanning. And in some cases, they're actually razor-cutting pieces of paper out of a newspaper and scanning it and trying to use OCR to turn it back into text. And that goes wrong as well, so you end up with scanning errors. So it's not all clean, nice digital data. It's got faults and problems. Now, if you get false hits, false positives, and one of our clients deals with a UK consumer magazine called Which, ? That's the name of the magazine, Which. Their previous solution didn't handle punctuation. They got quite a lot of false hits, as you might imagine. They cost you time. Your human operators who have to verify the relevance and post it onto the end client, it costs them time if they're having all these false positives. If you miss things, your customers will leave you, sometimes overnight. So if you miss a very important mention of somebody, you're in trouble. And the traditional approach is to get a load of servers, hundreds, and put a search engine on each one, split up the queries somehow, and then bring it all back together. So that's a traditional way to do it. But there's a better way of doing it. So this is a keyword, just to give you an idea of the sort of syntax we're dealing with. It's obviously something about tourism. This is a real one from one of our clients. And it's a syntax based on anyone heard of a search engine called DT search? Yeah, not many people have actually, but DT search syntax looks like that. And there's some interesting things here. You'll notice there's the top line is within 48. That's within 48 words. There's some wildcards. There's some stars, and actually there's some exclamation marks. If you look halfway down, we've got vacation. The exclamation mark is actually for handling OCR errors, scanning errors. We're looking for vacation or misscanned vacation. So there's a kind of wildcarding there going on for OCR errors, and there's stars, but a kind of wildcards. Here's another one. They get bigger. Some of these things are 3-page long Boolean expressions. They're not much fun to deal with, to be honest, but they can't be rewritten. So we have to cope with this syntax in whatever system we build. This is what the source data looks like. It's XML. I've cut it off. There's probably more text in that text field there. Sometimes it's a flavor of NewsML, which is a variant of XML used for news delivery. But they basically look a bit like this usually. But again, there may be some faults in there. There's some numeric information as well, but generally it's the text we're interested in, headlines. So what I'm going to do now is I'm going to hand over to my colleague Alan, who's going to tell you how we can do this. How can we take these 100,000 queries and apply them to every news article we see and get some matches out? How would we do that?
Hello, I'm Alan. Can you hear me? I apologise in advance. I've got a horrendous ear infection at the moment, so I can't speak particularly loudly, and I'm also on quite a lot of painkillers, so if I go on any particularly hallucinatory tangents, please pull me back. Right, so what you want to do is the opposite of a normal search. A normal search is you've got loads and loads of documents and you want to run a query over those documents and find which documents match that query. In our case, it's the other way around. We've got loads and loads of queries. We've got one document. You want to find out which queries match the document. So we create an index of a single document. There's a class in Lucene called the memory index, which does just that. You store all your queries in memory. So you've got a big long list of all queries that you want to run over this document. You run them one by one over the document, pull the matches out, and that's it. Very simple, very straightforward. Except it's not quite that straightforward because that does not scale at all. If you've got 100,000 queries and you're running 100,000 queries over every single document that comes in, that takes time. In Lucene, when you have a query, you can't reuse query objects over different documents. They have to be rewritten for each document because the things like wildcards or generally your multi-term queries need to be expanded expanded to cope with what's actually in the index at any one time. So for each new document that's coming in, it's a completely new index. The query has to be rewritten again. That takes CPU time. So how do we deal with that? You deal with that by cutting down the actual number of queries you run over each document. You want to reduce the query space that you're looking at. But at the same time, as you're doing this, you need to make sure you're not going to miss out any queries that would actually get a hit, because that's your false negative problem, and that loses you clients. Well, it loses our clients, which means that we lose them as clients. So, how do you narrow this down? Generally, what you do is you take the query and you pull out the terms that are in that query, and then say, okay, which of these terms are likely to match this document? We originally did this basically with a big hash map, and each term was in the hash map, and you look up all the terms in the hash map and pull the queries out of that until someone pointed out that that's essentially rewriting an inverted index really badly, and I already have an inverted index here because I'm using Lucene, so perhaps I should try doing that instead. So what we do is we create an index of queries. When you add a query to your query set, you pull out all the terms from that query, index that query against those terms. When a document comes into the system, it's indexed into the memory index, and one of the things when you create an index of something, that gives you a terms list. And so you take that terms list and create a big disjunction query out of that terms list. So say this document has got 5 terms in it. You then do a search against your index of queries for any query that also matches one of those 5 terms. You've got a specialized collector which you run, which you use to search your query index, and for every hit in the collector, it then runs the query against the incoming document, pulls out any matches if there are any, and this massively reduces the number of queries that you actually have to run, so it massively speeds everything up.
Well, what we're doing here is we're searching. The document is becoming the query, and the queries are becoming the index. There's confusing terminology here because we have queries of queries and indexes of queries and whatever.
Yeah, query documents and document queries. Yeah, part of the fun is working out what the best name is so that you don't look at some code and confuse yourself massively. So how do we index the queries? Well, term queries are pretty simple. You just take the term out. That's what you're indexing. Pure disjunction queries, you need to make sure that you are going to get a match on every single subclause. So you take every single subclause of your disjunction query and pull terms out of that and index that. For pure conjunction queries, that's an AND query, you can actually just take one term because every single subclause has to match. So you can find the simplest subclause and say, okay, we'll just index that. So you can throw away quite a lot of the query itself. Again, that reduces the number of hits you're going to get when you're running your initial search. So it reduces your query space a bit more. Positional queries, so X near Y, you just treat as an AND, as a conjunction query, and then you rely on the second stage here, which is actually running the query once you've got a possible match to tell you whether it's a real match or not. Numeric queries, in Lucene, numeric queries under the hood are exactly the same as a term query, so you just, again, index the numeric term. If you end up with a set of subclauses, so you've got a disjunction query and some of your subclauses there sort of end up with no matching terms, you still need to have something to index. So we have a special token called an any token, which means that, basically every single query is going to match against that. But you can generally rely on those appearing in the query tree somewhere within a conjunction. So generally they get thrown away, and you don't end up with many of those in your index. So there are very few queries you end up running which actually have to be run every single time. And things like numeric range queries, for example, will index like that. So it's very difficult to work out how to index every possible matching value of a numeric range, such that any possible how do I put this? Any document that could possibly fall within that range would automatically pick up that hit. So you just say, okay, fine, we'll just do it as an any token. But generally, numeric range queries are part of a conjunction. You don't normally say, I want everything that's on page 3 of a newspaper. You say everything that has text hello and is on page 3, in which case it's a conjunction query. You can throw away the numeric range part and just do the textual part. Regex queries are fun. How do you index something that's got wildcards in it? The way we have done it is you index the longest exact substring of your regular expression. So generally a regular expression has got some proper text in there, and then it'll have question marks or character classes or any of these things. You split it on the question marks, the character classes, anything that's a special term in the regex, take out the longest matching substring, and then when you're doing when you're indexing the document that's coming in, as well as taking all the individual terms in the document, you do n-gram analysis as well. So for the term hello, you also index the term HELL, HEL, EL, all the possible substrings, and then that will match against your wildcard query. The other thing we found actually is that quite often, well, in fact, most of the time, wildcards are done again as part of a conjunction query. So you can index it as an any token, as a match all token, but then throw it away because you'll have other terms within the conjunction that are more likely to match. This kind of depends on your query set and on your document set. So there are a couple of strategies you can use here. But obviously the latter one, if you can get away with indexing it as an any token, then you save a lot of time when you're doing your pre-search, because you don't have to do all the n-gram tokenization as well. So we need to make a few changes to Lucene to allow us to do this. There are a couple of minor ones. There was a bug in the memory fields that if you sent a null in for your field name, then it will blow up. The memory index itself was storing term offsets, but wasn't making them available, wasn't exposing them. So it did a bit of work to get that out so that you can access actual term offsets within the memory index. Most important one is this Lucene 2878, which has been sitting there in a branch for about 2 years now. Most of the work was initially done by Simon Villenauer. I took it over about a year ago, and it's moved on a bit, and then it stops, and then it moves on a bit again, and at some point it will get into trunk, I promise. What this does is it replaces span queries. I don't know if anyone's come across span queries in Lucene. Excellent. Yeah, it's a way of doing positional queries, so X near Y. The current implementation, span queries, it works fine, but span queries use up lots and lots and lots of memory. And if, as we are doing, you're holding sort of 100,000 queries in RAM, you want to make sure those queries are as compact as possible. Span queries are not compact. So this Lucene 2878 uses something called an interval iterator, which, can I explain how that works in the next 2 minutes? Probably not. There's a paper on it out there. It's an efficient way of working out whether particular intervals in a query are going to overlap or not. So it's an efficient way of doing proximity queries, essentially. Ask me at the end if you want to go some more details, and I'll see if I can remember how it works now. So there's two advantages to this. One is that they're more efficient, more memory efficient, and in fact more time efficient as well than span queries. So it gives us a general speed up in doing running all our proximity queries. The other is that it allows you to pull exact match positions out of the query instead of a score. So normally in Lucene, when you run a query, what you get back is a score. It's a number, a floating point number. But what interval iterators allow you to do is instead is actually to pull out all the intervals that matched on that particular document, which means that we don't have to run a highlighter over the result to find out where the match is. This is a good thing because highlighters don't actually tell you where the exact match was. It tells you where the highlighter thinks the match might have been. This gives you the exact, this is what the scorer actually matched, and that's important for our particular use cases. Clients want to know the exact match, not a kind of guess. Lots of you will be thinking, this sounds very much like the Elasticsearch Percolator. Why are you not using that? So part of the reason is, yeah, we have to do our own version of Lucene. We're actually maintaining a fork of Lucene at the moment, which will be there until I get it into trunk, which will happen. Repeated. So the Percolator gives out a certain amount of information. You can use a highlighter to get some data out, but you can't get, we'd have had to rewrite quite a lot of it in order to get this sort of information out, and it seemed to make more sense to sort of have our own module that would do it. And also the Percolator allows you to do things, it allows you to cut down the number of queries you're running by using filters, but you have to kind of define them up front. And you can't use the kind of dynamic pre-searching that we're doing here, which is, based as each document comes in, the pre-searcher looks at the terms list, works out which queries might match. You can't do that in the Percolator, so which means you don't get the same kind of speed up that we've seen here. Charlie wants me to reiterate this. The fastest way to run a query is don't run it. Okay, particularly if you know it's not going to get any matches, you don't need to run it. So yes, we've pulled out the interesting bits of this into a library, which we're calling Nowak. It's on GitHub. It is as yet a private GitHub repository because I haven't written all the Java docs for it yet. But in the next couple of weeks, that will be public. Works with the standard suite of Lucene queries, and you can add in your own query term extractors with your own. If you've got your own custom query types, you can tell Nowak how to pull out terms from that it can then use in the pre-searcher index. Each instance of Nowak holds all its queries in memory, so you can run lots of them in parallel. And the way we've got it working at the moment for a particular client is that they're using RabbitMQ as a document source, and so you can attach lots and lots and lots of different instances of this to that document source, and they'll pull documents off one by one. But you can scale it linearly just by spinning up new instances. They don't rely on each other at all. It's based on the fork of Lucene that I was talking about there with the interval iterators, but once that gets merged into trunk, then it will be based on just pure Lucene, and it will be available very soon on GitHub, I promise. Yeah, it's a very basic interface. You have a monitor, you add queries to it, you run match against a document, and you get some document matches back. It's pretty basic. You don't need to do anything particularly clever here. And the document matches object will give you every single hit that it's found for that particular query and some metrics as well. It's an example output for a client we're working on at the moment. Excuse me. So you can see you've got your statistics at the top. You've got prep time, which is the amount of time it's taken to build the pre-searcher query. As you can see, that's very, very quick. Query time itself, number of queries it's run. In this case, it's run one query, so it's not a particularly interesting one. But yeah, you've got highlights. So each term that it's hit tells you what the term was, where it appeared in the document. Hand back to Charlie now as I...
So how fast is this? These are from real world use cases. The first one, it really depends on how complex the keywords are. Again, some of the 3-page booleans, they don't end up very small in Lucene land. So, but these are some numbers we've got. We can apply 70,000 keywords a second. That's 70,000 if they're relatively simple, small queries. That was just tested on a pretty standard MacBook. We built this kind of thing before using another open source search engine called Zapier, which I'm sure many of you won't have heard of. It's a probabilistic engine. had a history going back to the early days of certain large Cambridge-based probabilistic search companies, some shared history there. And basically, this new thing was 20 times faster than our own implementation. For more complex keywords, things get a bit slower, but you're still looking at some pretty impressive numbers. And of course, you can scale this out for volume easily. So we basically got from hundreds of servers down to single figures of servers, really, in most of the applications we're looking at. So we're quite pleased with how fast it is. This is how we build LUAC, the core library, into the actual real-world system. This is different for each client. This is just an example based on a current client. Some of them have got a massive, great Oracle database that holds all their articles and their queries and everything. Some haven't. Some got more of a kind of workflow setups with pipelines and whatever. But this is basically how we built the most recent application of this. Some interesting bits here. The multiple instances we've talked about already. They have a database of queries which they maintain. Articles come in this NewsML, this kind of XML type format. Either you harvest them off disk or you get some kind of messaging system. Interestingly, we also build a pretty standard Solr index because for two reasons. One is so you can test new keywords against some recent content. So it speaks the same syntax as the monitor. And the other is some of the end customers would like to search last week's news occasionally. But that's kind of just a side effect, really. It's a pretty standard Solr setup. But remember, it's based on our patch version of Lucene. And it all uses RESTful Web Service APIs, so that's all modern and lovely and means you can wire things up nicely. So, what next? We got 3 clients currently running this or a version of this kind of setup. We're replacing systems built on DT search, I mentioned. We're also currently in the process of replacing one built on Verity. Verity has its own query language of VQL. Now, one thing I did gloss over is how do we turn that old syntax into Lucene syntax? So basically, we write some parsers. And what's happening currently is we're kind of ended up with an intermediate format. So we take the original, say, VQL for the sake of argument, turn it into something else, and then that gets turned into Lucene. Which begs the question, what other search engines can we replace? What other closed source engines could we write a parser to turn their query syntax into eventually a Lucene query syntax, or more sensibly, some kind of intermediate thing? So I've been talking to some people here about the idea of creating an open source query syntax that, a one syntax to rule them all kind of model. And then running that on Lucene is basically just an implementation of that. But the idea is, any other system you've got, you can translate to this intermediate syntax. There's some checks and balances. It's generally not 100%. You don't catch everything. There's always a few queries that are weird. One thing we found with Verity is if there's a syntax error in your Verity query language, Verity doesn't tell you, which is nice. So we were trying to replicate behavior that was always broken in the old system. But as I talked yesterday about a syntax called BRS, patents from the Open Source Connections guys, there are people I know working with FQL, fast query language. But if we could all work together on some kind of collaborative central syntax of doom, then hopefully migrations from one search engine to another will become easier. We'll have more people using Lucene, hopefully, because that will be maybe the reference implementation of this standard. But do get in touch if you think this is a good idea or a stupid one and tell us. We certainly like to work with other companies in the same position who maybe know a bit more about particular search engine syntax. We'd like to make LUAC a bit faster still. We know of cases where people have got a lot more than the 100,000 keywords or queries. We know people with in the millions, and who are dealing with hundreds of articles a second, processing a lot more content. So we'd like to be able to handle that situation with this. So probably the way to do that is to shard out the query set. So instead of every instance of LUAC having all the queries, we have some kind of sharding setup. That's the plan anyway. When we get to that point, if we get to that point, I don't know. But it can go faster. We'd like, obviously, to get this Lucene patch into trunk, so we're based on standard Lucene. Yes. And then what other things could we do with this LUAC library? Well, for example, you could use it to add metadata to items based on an expression. So if item matches XYZ in some way, add this bit of metadata to it. So you've got some kind of content-based system there. You could do classification with it. You've had a taxonomy, and each node is defined by one of these kind of keywords or queries. And you could do very fast classification. We've actually got a prototype taxonomy GUI app that we built for someone else, and we'd like to put the two together. It's called Clade. You can find it on our Flax blog. And that's an example of how you browse a taxonomy and you classify things into the taxonomy. So we just need to add to the LUAC, to the Clade, and we've got a nice taxonomy classification system. But you tell us, if you can think of a cool thing you'd like to do with LUAC, then we'd be very interested to hear about it. From the things I've heard here, a lot of people are doing similar kind of things, but performance-wise, ours seems to be a lot faster. There are certainly people looking at similar end use cases, but they're doing it more in a kind of just, let's just get lots of servers and spread things out and do it that way. But yeah, I think there's some interesting things we could do with it. Documents per second. Yeah, I think it's something like 2,000 an hour, is that?
Yeah, I mean, it's on the order of 1 doc per second with the client who's got 90,000 queries in there. But again, it depends on the complexity of your query set and how big the documents are and everything. So, yeah. And that's a single instance as well. So the idea is that you scale it out by just spinning up more instances. So if you double your speed, double the instances.
Yeah. Yeah. But these particular situations, they get a pile of news articles in the morning and they get more during the day. So as long as they process all of their articles in that day, that's fine. There's only one endpoint. There's only one thing being sent to the end client. So we don't have that kind of requirement to be any quicker than that. And again, it's solved the problem. I mean, with some of the, there were some odd things going on at some of these clients where, for example, they were loading Oracle so much in their old setup, and that was costing them lots of Oracle time and Oracle money and more Oracle servers. So actually putting this stuff in reduced their need for quite so much Oracle, which saved them lots of money. Of course, a lot of people would rather not have to use Oracle, but they do. So there are other sort of side effects in terms of cost reduction.
Yeah, the nice thing that the current client are doing actually is they know they have sort of waves of documents coming at certain times of the day, and because they're using Rabbit as a queuing system, they can just spin up new instances, attach it to the queue, and it will, for certain times of day, you can say, all right, okay, today I need 20 servers running at this time, but the rest of the time I'll just shut it down. And if you're using something like Amazon, then you pay for the time per server.
You could dynamically spin things up. Another bonkers idea I had was to do this for Twitter, but to actually make it all controlled by Twitter as well. Would be quite fun. So you'd basically ask something by Twitter and say, create new queries by tweeting them. I'm not sure that's a sensible idea at all.
It's a good way of making sure they're not too complex, because they have to fit in 140 characters.
Yes, that's good. We're only allowed small queries. But we're beginning to be able to handle quite a lot of queries here. So that's basically it from us. Does anybody have any questions? So the question was, if you want to use LUAC but not get all the positions information, just a match, just a Boolean, so it matched or it didn't, would that be something you can separate out easily?
Yes, I'd probably need to do a bit of work, but yeah, certainly one of the things I'd like to do is create a separate branch of it, which is running off Lucene trunk, that doesn't get you those exact positions. And yeah, that should be pretty doable. Yeah, I mean, one of the advantages of using so you would miss all the advantages of being able to throw out span queries. So you would have to, you use more memory and you lose some of the performance, but it's certainly possible.
How are we doing for time? We're done. Thank you very much. If you've got any questions, any technical questions, ask Alan. Any not so technical questions, ask me. And I thank you very much for coming. I hope you enjoyed it.